previously we talked about low pass filter and high pass filter, how resistors and inductor and capacitors are all connected series or parallel. We discussed about it. So now we go in more in depth into connecting high pass and low pass together. Okay. So if you connect high pass and low pass together, you're gonna create different things. So what are the things that you can create? So if you put high pass and low pass in series, you're gonna get a band pass. Okay, so you're gonna get this dude over here. So if you were to connect in parallel, if low pass and high pass connect in parallel, you're gonna notch filter. So you may wonder what is band pass and what is notch filter. So notch filter, good question. So in other words, if you were to have a band pass, your high pass and low pass gonna connect in series. Or if you have a notch filter, your high pass and low pass gonna connect in parallel. And then for advantage and disadvantage, I believe that they're all the same. Okay, because you're gonna select different types of because at this point you're selecting the frequency to on, right? If you remember, you're selecting this dude to on. This is, you can have a very narrow range of selecting frequency for band pass and notch filter. So you select this frequency to on, or perhaps you select this frequency to do something lah. But nonetheless, for notch filter, you select this frequency to off something or to put down something or something like that. So these are they have the both advantage. So they are both disadvantage is actually their inductor are creating magnetic problems, which may affect the, like, creating a noise or whatever. So it may affect the signal wise. So later on we will talk about gyrator in the op-amp filter, but now we only focus on the notch and the band pass. Okay. So in band pass there is three types of connecting band pass. Okay. So it's a little, yeah. So for the first one to connect band pass, just take note that everything are connect in terms of series. Okay, if the questions ask you only for like 2 marks, I think you can just straight away put this one. If it's like really cause you to write draw 3 type of band pass circuit that you can draw 10 marks, and you are xiao liao. So you're gonna draw this one. So the first one you're gonna draw is actually low pass filter section. If you remember, this one is actually the low pass, and then this one is the high pass. Okay, high pass wise is the capacitor. So this is mainly on capacitor only, right? As you can see, this is mainly on capacitors, all are capacitor and resistors. So these are all RC band pass. Okay, if you were to have a RL band pass, you're gonna connect in this manner. Okay, so make sure you go and take note about it. Nonetheless, they are connected in ways that are similar. Okay, I don't know whether they are connected in ways that are similar. But this one is low pass and high pass. This one is high pass and low pass. So you're gonna take note of this configuration, right? So if you doubt me, what I can do is if you take a look at this thing over here, this is actually low pass, right? If you take a look for low pass, you're connecting parallel to your high pass, right? So it's some resistors, capacitor at the middle, and then you have an R load. So in this case, you're connecting your resistors and your capacitor in this way, and then you have another, like capacitor and R load over here. Yeah. So if for high pass, capacitor and the R load are connected in series, right? So when I think you get what I mean already. So I didn't show a feeling lah. So in other words, just to take note that this is RC band pass. This is RL band pass. Purely capacitor, purely inductor. Okay. So if it's later I think I don't know whether I need to go through these. This case I would recommend later I'll go through, but I recommend you can also watch this video. Just type in all these things. AC circuit resonance. So you are connecting. So for the second configuration, you are connecting the capacitor and the inductor in parallel. So if you're gonna connect in parallel, what you're gonna have is actually in how do I say it? I don't know where I'm talking about, but let's go back to connecting the inductor and the capacitor in parallel. When you connect in parallel, you're taking XC is equals to XL. Okay, you're saying that they are both the same. Okay, so this is the meaning. If you want to ask me, you just head back to the video over here and you watch. Okay, and then if I were to rearrange, okay, I bring this 2 pi fc upwards. I have 4 pi square, so 2 pi times 2 pi, 4 pi square, and then fc f square cl. So if you were to rearrange, I bring the f pi, 4 pi square, and cl downwards. Okay, and I bring the square root up over here. You'll get 1 over 4 pi square cl. Right? If I were to simply bring this one over down here, and then I bring this one down here, I have 4 pi square cl, right? And then I bring this square root over here. This is where I have. And then if I were to factorize out, okay, if I were to do a little rearrangement, I have 4 pi square cl equals to f. And if I were to factorize out the 4 pi square out on the square root, I have 2 pi, and I have square root cl is equals to frequency. So this is the formula that is given inside your chapter 8, I think. Where is it? Yeah, I think it should be here. The equation, yeah, is over here. So this is the equation for the advanced filter. Okay, in the sense that they are connected in parallel. So with this said, after thinking a long time, okay, if we were to merge, so in this scenario, right, this scenario XC is equals to XL, this one is, it reflects this point over here. When the frequency, when the inductance and the capacitor shares the same frequency, okay, they actually have a infinity impedance, which is damn high, which is over here. Alright? So if your frequency is so-called like lower, okay, if your frequency is somewhat because as you know that this is the frequency axis, right? So not necessary that the frequency must be damn high in order to reach that top value. It's just when the capacitor and the inductor reach the same point of the frequency, then they will spike. So this is the beauty of it. And then as for if it's a high frequency, they work differently now. As for high frequency, the inductor itself, it works as a what do we call? So the inductor itself, it works as a low high pass filter. Yeah, whatever. So if frequency is high, it acts as a high pass filter, which is damn. So if the frequency slowly increase, right, it's gonna go in this manner. And then if the frequency is gonna go down, and then capacitor we're gonna kick in over here, and then it gonna comes down. This is not a very good explanation, okay, but because they both work together as a parallel circuit, so if you want to calculate, it's very cheap, okay, it's very troublesome. But the keynote I want to convey here is there's 3 things, okay. It's either frequency high, okay, hold on, okay, yeah, if frequency high, okay, you're gonna have it's gonna go down, okay, it's gonna go down. So if the frequency is low, you're gonna have a thing going up. And if the frequency is, if XC is equals to XL, equals to your frequency, maybe, yeah, it shares the same frequency. This is the point where it's the highest voltage. Okay, so normally the question will ask you what is the highest voltage of a band pass. So you're gonna use this formula. over here. And how do you derive this? You can equate xc equals to xl, and then you rearrange, and you can get this equation. So now this is only the second configuration. Okay, the third configuration is when you put the capacitor and the inductor in series. Okay, if you put it in series with the R load, you'll get this dude over here. So in this case is a little different. Okay, how are they different? The calculation wise is the same. Okay, 0 plus j 100 ohm and minus j 100 ohm. If you don't know that the inductor itself, if you remember, it's plus 90 phase, and then for the capacitor is a minus 90 degrees phase. So this explains why it is because in other words, this is also xc is equals to xl. Okay, they share the same frequency. Okay, but however, one thing is that when they're connected in series, the outcome is that if you were to add them up together, you also have a 0 over here. Previously it was 1 over if it's 1 over, previously it was 1 parallel is 1 over 0, right? You have infinity. But in this case it's 0. Okay, you allow this whole piece of inductor and capacitor to become a so-called open circuit. Short circuit. Short circuit. So in other words, there will be no resistance at all. So in other words, this is gonna flow through like a boss. Okay, so you're gonna flow through, and all the voltage will flow all the way to the R load. Okay, because this thing simulates this R load. What is the voltage across this R load? So this is a very key concept that I didn't realize. So this graph itself simulates that. In fact, all graph you see, right, all the voltage graph, all this, all talking about the amount of voltage going through the R load itself. So this is the key concept that you need to understand in order to typically understand everything. So this is the three method, okay, in creating a bandpass. The first method is you take whatever you learn for RC and RL, okay, then you just put them in series, then you can have a so-called a bandpass filter. What the fuck? RC bandpass filter. And then this is RL bandpass filter. Okay, so this is one method when you're connecting them in series. Okay, another method is actually to connect your inductor and capacitor in parallel in order to have this dude over here using this xc equals to xl. So xc and x equals to xl can be applied to this one and this one. Okay, so you can connect your inductor and your capacitor parallel or series. Okay, it's no problem, but the explanation is a little different. So I hope I give you a very clear understanding of this. In fact, it's 4 lah, okay, but they are in the same category. So yeah, the 3 types of how to combine and create a bandpass filter. So yeah, so good luck, and I'll talk about it on the notch later. So I'll see you there.